Swayam Prabha. Digital India. Educated India.
Okay, so we will complete the gas radiation problem involving a spherical cavity where we had a mixture of carbon dioxide, water vapor and nitrogen, which was a 2 atmosphere. 41 problem number 41. $400 Kelvin, right? It's a black wall, right? Huh? I gave it to be a black wall, right? So, yesterday we looked at the charts repeatedly and arrived at the epsilon g, that is the emissivity of the gas. So, epsilon g was 0.36. Huh? Now we will have to get alpha g. Yeah, the first step is to get can you tell me all these values? So, you have to basically employ the same procedure, except that there will be a normalizing factor called Ts by Tg, which takes care of the ratio of the two temperatures, and you have to apply use the same charts. Yeah, shall we go one by one? What was the absorptivity of the carbon dioxide? Did we work it out yesterday? Okay, 0.025. The correction factors are the same, right? That's already where did same correction factor is to be used, no? What are the correction factors? 1.1 and 1.57. What is it? Okay, so we got this. Delta alpha we worked out yesterday, right? That was easy. Okay, just get me the alpha of the water vapor and we are done. So delta alpha is almost 0, right? Very small. You can use that. Okay, so we use the same charts. Okay, gas emittance for CO2, the same chart we use for getting alpha of CO2. Page 2, page 3, we get alpha of water vapor. So you have to find out the PC into PW into LM, and then get the gas temperature and then get the alpha W. How much was it? Alpha W 0.15, is that correct? Others please check this. Alpha
C is equal to CC into epsilon C plus into correction factor for detector.
No, which correction factor to compute it? Yeah.
This is multiplied already.
No. I didn't want you to tell me that. This is alpha C from the chart. Okay. I want this from charts. Okay, don't go to the. From charts, what are the values? 0.02, alpha whatever should be high. I expect it to be 0.3, I expect it to be high. 0.3, Vikram, I am not, I don't want the post process values. I don't want the post process values. We are doing step by step. Okay. So show me what formula did we write yesterday?
CC into epsilon C plus.
Huh?
Alpha CO2 was epsilon C plus into CC into this temperature action.
This is epsilon C plus is basically?
For as defined for this one.
No, that CC was not there. That we are already calculating, no, based on that. No, there is a notational problem here. I gave you alpha C equal to epsilon CO2 plus into Tg by Ts to the power of, okay. Okay, so shall we put this as star? Huh? This, no problem, this is actually epsilon of CO2 and this thing got the corrected temperature, that is all. Huh?
You have to use these scaled up parameters while you're finding the alpha itself from the chart.
Yeah, and then but then we are again multiplying by Tg by Ts.
0.02, 0.09.
Yeah, you guys are, no scaled up. Okay, I want only the directly from the chart. First directly read from the chart with Ts by Tg and tell me. Then we will go step by step. Nah? Directly from the chart, what do you get?
That is 0.04.
Which one?
After that you multiply the Tg by Ts
No, leave it.
and the correction factor.
No, I don't, before multiplying by correction factor, before everything. Huh? 0.4 this one?
From chart multiplied by the Tg by Tn.
Don't multiply anything because somebody else is seeing the program. So first reading from the chart, what is the value? We will multiply step by step. No? Don't. Yeah, that is fair. You have F6, F7, whatever I have given, that has to be multiplied. Correct. Corresponding to that alpha u. Huh?
That is 0.09.
Point not? Which one?
Alpha C.
Okay, alpha W. Okay. Correct, alpha C plus multiplied by that power, yeah, what is this now? This is the procedure, okay. First get without multiplying any scaling factor whatever, likewise this will be Tg by Ts to the power of 0.45. Because I was expecting an alpha of W of 0.6. Are you getting? Okay. Sorry, alpha G of 0.6. If I have given the formula, that is, if I have given the correction factor afterwards, you take care of. Do not do the correction factor twice. At the same time, do not forget to apply it once. Okay, basically it is like that. The correction factors have to be applied once. Tg by Ts to the power of 0.65 and 0.45 have to be multiplied once, and then Ts by Tg has to be taken for reading the charts. Only 3 principles involved. LMT, LM into PC, that is all, right. Do not do something twice and do not omit. Vamsi, is it clear? Finally, what was this? 0.6, huh? Sampath, what is it? Alpha W, alpha G, 0.6, 0.6, 0.64. Why?
0.64, sir.
Oh, right. So the most important thing you realize is epsilon G is not equal to alpha G. Okay, epsilon G is not equal to alpha G. It is not a grey gas. We cannot simply calculate epsilon G and proceed with the calculation. So we will be stumped. So the mixture of carbon dioxide and water vapor is a non-grey gas. Okay, that is why it is good that these people Hotel develop these charts. Now we can solve the equation of transfer numerically and get this. Okay, but this was done in 1945. Lot of things developed during World War II, including war, right. Okay, so now we got the, what is the cooling rate required to maintain this fellow at 500 Kelvin or 400 Kelvin? 500 Kelvin. That means we want four pi r squared. Is that correct? Sphere. So this is the cooling rate required to maintain it at 500 Kelvin. Now J1 is easy. One is the wall. There are no two surfaces in this enclosure. It is only a single surface enclosure. I gave black wall, isn't it? Okay, fine. How much is this? Okay, leave it. Shall we derive the generic formula first? Okay, we will derive the. Now what is G1? It is gas radiation. Epsilon G Fij Jj tau Ij. There is only one enclosure. There is only one surface. Okay, the other one is gas. Therefore, and F12 is not there. F11 equal to 1. The sphere sees itself fully, and tau 12 can be taken to be tau of the gas. Correct? You can call it as tau G. Therefore, plus so now what is this tau G? We cannot put 1 minus kappa L12 by because that was for grey gas and all that.
1 minus R.
1 minus alpha g. We did so much struggle we undertook to calculate alpha g, right. So we can say that because alpha g plus tau g plus rho g equal to 1 for the gas also, we do not worry about this fellow now. Therefore tau g equal to 1 minus alpha g, therefore so if it is a single surface enclosure involving gas radiation, if it is a mixture of these gases, right, in the exam you can straight away use this final formula, you do not have to derive. Alpha g sigma t to the power of 4 minus epsilon g sigma t g to the power of 4. This is a standard formula, it will be given in several textbooks, but we derived it using enclosure theory in today's class, correct. If you see book by Holman or Uzisik, he will work out gas radiation problem straight away by taking this formula. Okay. Yeah, put in the values, get me the value of Q1. What is alpha g? 0.64. Yeah, so you got alpha g plus epsilon equal to 1, is it? That is strange. Okay. Need not happen always. Yeah, kilowatts minus. Of course, it is minus, isn't it? Minus, sure. Kilowatt per meter square, is it correct? I did not reverse. 138 kilowatt. Okay. Q1 you are not getting that, Sampath? Thousand 400, okay, minus 76 point. So Q equal to so what does it tell you? What does it tell you? We need to cool, that is okay, it is pretty straightforward. Otherwise this fellow will get heated, he will also reach 1500 Kelvin provided an inexhaustible supply of gas is available. More importantly, in this spherical cavity, if you put ethane or propane or LPG or butane, burn it, allow it to reach a temperature of 1500 Kelvin, okay, and you get a mixture of CO2, H2O and N2. It is possible to send tubes, it is possible to put tubes on the outside of the spherical cavity, send water and heat water at the rate of 60 kilowatts. This is the power which is, this is the radiative heat transfer power which the gas is capable of transferring to the wall. So this is, as you can see, this will be very important in furnace calculations, design of radiant superheaters and stuff like that. So it is important in, so it has got engineering applications. Okay. Of course, you have got if different surfaces are at different temperatures, some of the surfaces are insulated and all that, then we are going to be in a lot of trouble. That question will arise. Tau of 1 to tau g, which from which Ts by Tg is with respect to which surface and all that. So we will stop our calculations based on gas and one surface, that is all. Okay. So this brings us finally to the end of radiative heat transfer. So it has taken 3 months. So 3 out of 75% of the course has been radiation, but I think we did about we had 34 classes. I think you got a good account starting from radiation loss to radiation properties, then view factors, then enclosure theory for non-gray stuff, where we used spectral radiosity distribution and a band model. Then we introduced the equation of radiative transfer, gas in absorbing and emitting medium, and we got analytical solutions to the equation of transfer, solved simple problems like in 2 parallel plates, and then we found out what happens for the case of a radiative equilibrium, and then how to calculate emissivity and absorptivity for a gas mixture, how to apply it in a engineering problem. So the last few classes what we have seen basically comes under the category of engineering treatment of gas radiation, because this is an engineering treatment. It is a recipe, it is a very quick way of solving problems by using charts, getting the properties, and this the complete detailed way would be to solve the equation of transfer for various spectra and then work out the gas. There is no need to define an overall absorptivity and transmissivity in that case. Then you will work out the intensity or the flux in each of these intervals and integrate. Okay. Now we will finally start conduction heat transfer. So we will have about 9 or 10 classes. Let us see what we can do, because conduction itself I can teach for 45 hours, right. So it is also an exhaustive subject. Now this class we will just see the introduction. I will make this material available on Moodle by Monday. Okay. So did we see the introduction to the 3 modes of heat transfer in the first class? I explained to you about conduction, right. Okay. So heat transfer is basically energy transfer between 2 bodies solely due to temperature difference. Okay. However, that has to be taken with a pinch of salt, because radiative heat transfer will take place even when temperature difference is not there. Radiation will take place so long as temperature is above 0 Kelvin. Okay. So applications are I mean the applications of heat transfer are far too many, starting from microscale boiling to space radiators. The applications are legion. Importance: the design of heat exchangers, energy conservation devices, cooling of laptops, cooling of personal digital assistants, cooling of iPad, iPhone, cooling of data center, cooling of Cray supercomputer, okay. Then cooling of the re-entry vehicle such that the inside compartment is okay for the astronauts. So everywhere, even there is the lung is the best mass transfer device, right. It gives a maximum surface area for a given volume. You must have seen in your heat transfer course that an important performance metric for the compactness of a heat exchanger is how many meter square surface area is available for per meter cube. Nobody can beat the lungs, no device can beat the lungs. So right, so there is heat transfer everywhere. Okay. So this is basically the importance can never be overstated, because it is very important. Okay. So the relationship between heat transfer and thermodynamics we have already seen. So Q is one of the 3 terms which occurs in the first law of thermodynamics. Q is an interaction occurring at the surface, W is an interaction occurring at the surface. The difference between these two can be explained by a property called energy or the change in energy, right. if for a closed cycle the energy need not be introduced. So you introduce the concept of energy for a non-cyclic process, similarly you introduce the concept of entropy for a non-cyclic process. Okay. So the foundations of heat transfer are based on both theory and experiment. The foundation of any science will be based on both theory and experiment. The theory is basically physical laws in terms of various concepts based on experimental observations. So we have two types of laws, the general laws which are independent of the medium and particular laws which are dependent on the media. So the general laws which are applicable for conduction heat transfer, basically the law of conservation of mass, the first law of thermodynamics, second law of thermodynamics. You can say A, B, C, D are applicable to all heat transfer problems. First law of thermodynamics, second law of thermodynamics and Newton's second law of motion. Second law of thermodynamics is not very frequently used in heat transfer, it gives us the direction of the flow of heat, but second law analysis can be used for several heat transfer systems to find out whether you are doing certain things efficiently from the entropy point of view. Okay, so every system has an associated entropy generation, right. So whether you are minimizing the total entropy generated in a particular process or in a device, basically if you do that it is the second law. You can see that the first law and second law would be sufficient, it would suffice for most conduction problems, because invariably there is no mass entering and no which is mass which is leaving the system in a conduction problem, and then the Newton's second law of motion is not there mostly. Can you give me some examples where the body is moving in a conduction problem? The body is moving or the heat source is moving. The heat source which causes the conduction or the body is moving, but no convection. The re-entry vehicle or a space application whatever, so the body is moving, there is a velocity, and then you have got a convective boundary condition or the boundary condition will come because of mv squared by 2. Mv squared by 2 is stopped and is converted to kinetic, converted to enthalpy on the surface. So these applications the body is moving. Can you give me some applications where the source is moving? If you are welding and you are moving the welding rod, that is where the heat source is there. So it is a moving heat source problem. Okay, it is a moving heat source problem. So there are problems in which the heat source or the body move, but these are exceptions in conduction heat transfer. The general rule is that the body is not moving. The particular laws are three laws: the Fourier's law of heat conduction, Fourier's law of heat conduction basically for conduction heat transfer, the Newton's law of cooling for the convective heat transfer, and the Stefan-Boltzmann's law of radiation for the radiative heat transfer. All these are particular laws which are not universally applicable, right. They are applicable only in specific situations. So if you apply the Fourier's law of heat conduction and the Newton's second law on to your first and second law of thermodynamics, it is possible for you to derive the general heat conduction equation. Okay, then finally you can say that the body is not moving, that will give rise to your Poisson equation, Laplace equation, then one dimensional heat equation and so on, right. It is possible to apply Fourier's law of heat conduction and Newton's law of cooling to the law of conservation of mass, first law, second law and Newton's second law of motion. What do you get? You get the Navier-Stokes equation, you get the Navier-Stokes equation and the equation of energy. Okay. Radiation we do not do, radiation is separate. Please remember that the equation of transfer is not an energy equation. Even the problem which we solved in the last class, there is no equilibrium there. That means the RT equation is not a standalone equation, it gives rise to a source or a sink, right. So it has to be solved in conjunction with the equation where some property is conserved. Are you able to appreciate? So in a combined conduction radiation problem you have to solve the conduction equation, there will be a source term for radiation. If you want to calculate that source term, you have to stop the conduction calculations and do your radiative calculations and go back. Okay. So if you combine this particular laws with the general laws, you get new subjects. Okay. If you combine these laws with this, you get conduction heat transfer. If you combine this with this, you will get convective heat transfer. If you combine this with this, and you will say that di by, you have the equation of transfer, you have radiative heat transfer. So basically So these are what are called the constitutive equations, the constitutive relations insofar as the subject of heat transfer is concerned. These are general laws. So every subject will have a field of, will have some experts who draw upon the basic laws of nature, apply equations which are applicable to their media, and then come out with a science. But still it is all Newtonian physics. So we can still say that heat transfer is still mechanics and thermodynamics we want, right. We are not still trying to solve the Schrodinger wave equation or quantum mechanics. Of course in radiation you do that. Most convective and convective heat transfer still it's Newtonian physics, okay. So we should not say this at the fag end of the course, everybody knows that there are 3 modes of heat transfer: conduction through elementary particles, convection is advection plus bulk motion, but advection plus conduction. Radiation does not require a medium, it is best in vacuum. So some people skip point number 2 and say that there are only 2 modes of heat transfer, conduction and radiation, okay. So elementary particles at high temperature regions at higher energy level oscillate, so then there will be a microscopic movement of molecules. So at a particular layer some molecules from top can come to the bottom, from bottom they can come to the top, but there is a temperature difference. So though the number of molecules coming from the top to the bottom or the bottom to the top microscopically, even though there is no macroscopic movement, is the same, the energy carried by the particles with a higher temperature is more compared to the energy carried by the particles with a lower temperature. Therefore there is a net positive transfer of energy in the direction of decreasing temperature. That is a mechanism of conduction which can be easily explained in the case of gases. You can also extend this to liquids. For solids it is more difficult, valence electrons and all those things will come into picture, okay. So if you look at energy transport by heat conduction, that is the thing, oscillation transfer to neighboring particles, phenomena propagates through the medium, right. What about the measurement of heat transfer? Why are we always talking about a measurement of temperature and not about measurement of heat flux? It is possible to construct heat flux gauges, come up with the heat flux gauges and so on, but it is a lot easier to measure temperature, because there are various ways of measuring temperature. You can use thermometer, thermocouple, thermistors, optical methods. One of my students is working on liquid crystal thermography, okay. In liquid crystal thermography what you do is you have a sheet and paste it on the surface whose temperature is changing, where there is a temperature distribution. The color of the sheet will change depending on the temperature. Then you take a picture in a high speed camera or a CCD camera, then convert the colors to temperatures, and then you get the temperature field. From that you solve additional equations, you solve inverse problems and so on. That is liquid crystal thermography, right. So there are various, temperature is a lot easier to measure. So then what we do is, okay, sometimes we want to know the temperature, we want to know whether the temperature, the maximum temperature in the laptop respects the standard set by the manufacturer. What I mean by respect the standards is, okay, if it should not exceed 80 degrees centigrade, it should not exceed 80 degrees centigrade. But oftentimes you are interested in the flux. If you are interested in the flux, what you have to do is you have to first measure the temperature and link this temperature gradient to the heat transfer rate, okay. So this through the Fourier's law of heat conduction, when q double prime equal to minus k delta T, okay, it is basically a rate law applicable to conduction. It is not such a great law that it cannot be, in the sense that it cannot be proved from first principles. Whenever conduction heat transfer takes place, the heat transfer rate is always proportional to the temperature difference, is inversely proportional to the area, and if you replace a proportionality constant by inequality, you get what is called the thermal conductivity. Therefore the thermal conductivity of a medium is nothing but the heat flux, and the gradient of the temperature is unity, that is all. So the Fourier's law of heat conduction gives you an operational definition for K. It gives you a way to measure K, okay. So when you are actually trying to measure the thermal conductivity in a lab, did you do the thermal conductivity measurement? No. When you are actually trying to measure thermal conductivity in a lab, you use what is called a guarded hot plate apparatus. There are 2 plates, they are maintained at different temperatures, and then you send a certain amount of heat flux and find out the 2 temperatures, okay, or for the 2 temperatures what is the heat flux which is occurring. Then you take the delta T can be put as dt by dx or delta T by delta x, you estimate the k. So this simple measurement of k, what you are actually doing is you are solving an inverse problem, okay, because if you know the thermal conductivity, you can take the conduction equation and predict the temperature distribution or the temperatures at the two boundaries. But what you are doing is ulta, the reverse. I am giving you the two temperatures, turn around and tell me the thermal conductivity. So this is a very simple case where in a straightforward way you can get the k. But if the k itself is varies, kx is different from ky, is different from kz, you require a lot more work. So this comes under the subject area of inverse heat transfer, okay. So this is the heat flux vector, this is the thermal conductivity, is a thermophysical property, and T is the temperature. So for metals, the thermal conductivity is the order of 10 to the power of 2, okay. For insulators it varies from 10 to the minus 2 to 10 to the minus 1, gases it varies from 10 to the minus 3 to 10 to the minus 1. I will give you a table, okay. So thermal conductivity of selected materials, aluminium, the pure aluminium is about 190 watt per meter per Kelvin. Normally we use some aluminium alloy, so safely you can assume usually around 200, aluminium is around 200 watts per meter per Kelvin. Copper has a terrific thermal conductivity, 390 watts per meter per Kelvin. As far as heat transfer is concerned, it's gold for us. Copper is a benchmark in several cases, right? Copper cables, we use copper everywhere. It's also, that's why it also gets stolen. That brass also gets stolen. The Indian Institute of Technology, the Indian was stolen, because Indian can be easily resold. The ingate, okay, stolen, main gate, huh? Let's see when. Okay, metal, okay, okay. So so that is the story about metals. Steel, the thermal conductivity of steel. Steel, I cannot put steel, there are so many types, you must have studied your metallurgy courses, you have got mild steel, stainless steel and high carbon steel and so many low carbon steel, there are many varieties of steel. It is a ballpark or an approximate figure for 46 watts per meter Kelvin, 46 watts per meter per Kelvin. Non-metals, cork is terrific, cork is almost close to that of air, so it is an excellent insulator. Cork 0.042, thermal conductivity of air is 0.03, so it is almost close to air. But you can, I have put silicon basically because you should not be under the impression that any non-metal will have very poor thermal conductivity. Silicon has a good thermal conductivity. Glass has around 1.2, asbestos is 0.151, asbestos is now banned, correct, because it is carcinogenic, asbestos you cannot use. Air from kinetic theory of gases, you know that the thermal conductivity of air will keep changing with temperature. So this is for some particular temperature 297, 0.026, carbon dioxide is 0.0167, O2 0.16, oxygen 0.02, hydrogen is 0.182. So if you see air, CO2, O2, they are all 0.0 something, okay, they are very poor conductors. So the expression for heat flux is very important. So if this is your isotherm, that is your constant temperatures, right? I mean, so 100, let us say 100 degree centigrade, 90 degree centigrade. At this point you draw a tangent, so the heat flux vector will be like this. So, sorry, what, correct, the heat flux vector is normal to the heat flux vector is orthogonal to the isotherm, okay. Let us take a simple problem. Just to illustrate the concept, huh? let us say conduction in a plate, okay. What should be the temperature here? So 1D problem, no heat generation, nothing, constant properties. What do you expect the temperature to be? 75, okay. So this will be T of x, okay. So isotherms are like this, it is not properly drawn, everything should be vertical. So this is the 100 degree isotherm, 100, 90, 80, 70, 50, 40, no, 100, 90, 80, 75, 65, 60, 55, so it should be like this. So the heat flux vector is orthogonal to the isotherm, okay. So if you consider a problem, all of you have studied basic heat transfer, right? Let us consider a square slab. Correct? The governing equation is del square T equal to 0. What is this? Laplace equation. Suppose I say this wall is at 100, all the three walls are at 0 degree centigrade. How will the isotherms look like? Isotherms, not other way, okay. So we will start like this, please follow me. The 100 degree isotherm is this, the 0 degree isotherm is this. All temperatures are between 0 and 100 in this problem, correct. So the 90 degree isotherm will be like this, the 80 degree isotherm will be like this, 70, and finally this fellow is 0, okay. So 90, 80. Now I leave it as an exercise to you, please plot the iso heat flux lines on this, because the heat flux lines have to be orthogonal to the isotherms, okay, fine. We can discuss at the end of the class. So the heat flux is evaluated like this, orthogonal, and the heat flux is a vector, temperature is a scalar, heat flux is a vector. So it has got three components, qx, qy and qz. So the qx is given by minus k dt by dx, minus k dt by dy, minus k dt by dz. Why is the minus coming? To take care of the fact that heat is always flowing from a high temperature to low temperature, okay. So this q can be broken down as qxi, qyj, qk, qz of k, and where qx, qy, qz are the heat flux components in the three directions, and it is given like this. So it is the components of the heat flux vector normal to the isothermal surface, okay. So you can say that the dqa is basically, this is watts per meter square. So the elemental heat transfer rate is equal to the flux into the elemental area. So q can be replaced by k del t using the Fourier's law, and then therefore q must be integral dq over a. Then you can do this k into del t into n, where n is a unit vector. Then for the special case of a rectangular slab, if the temperature distribution is one dimensional, that is t is a function only of x, so this will become k dt by dx, and if k is not a function of x, k can be taken outside, so the q becomes minus ka dt by dx. Under the special case when the temperature distribution is linear, this can be written as ka delta t by delta x, okay. So this is a simple expression which you have used, I think from high school onwards you have learned this, okay. So please note this, very important. If the temperature is decreasing along x, then the heat is flowing from left to right. If the temperature profile is like this, heat is flowing from right to left. So you must get an idea of the direction. Okay. So the direction is given by the second law of thermodynamics, which forbids flow of heat from a temperature, from a low temperature to high temperature without the application, without the aid of external work, right. So please note this. So dt by dx is less than 0, heat flow will be, please remember this problem, temperature is decreasing along x, therefore heat must be flowing from left to right, and this is exactly the opposite for the other case. Now there are some materials which are anisotropic. Okay. An isotropic material is one in which the thermal conductivity is independent of direction, that is thermal conductivity in x direction is the same as y is the same as z direction. If kx, ky, kz are dependent on the direction, it is called an anisotropic material. A homogeneous material on the other hand is a material in which the properties are independent of position. So in this case, in this room for example, if you take an air sample here and measure the density, and you can take an air sample there and measure the density, if the density is the same in both the places, then the air is homogeneous. Okay, but thermal conductivity, but isotropic is if you are measuring a transport property with in x direction, y direction, z direction, and you get different values, then it is anisotropic. Okay. Now for anisotropic materials, qx, qy, qz, each of these contains 3 components. Okay. So you have qx is kxx dt by dx, kxy dt by dy, and kxz dt by dz. Like that, it follows for the other 2. Now, so the heat flux is related to the temperature gradient through something. This is called the thermal conductivity tensor. This is called the thermal conductivity tensor. Okay. It has got 9 components. Along the principal axis, main diagonal, you have got kxx, ky, kz, and you have got, because of symmetry, kxy, kyz, kyx, kxz, kzx, and so on. So it has got 6 elements which have to be determined. Other 3 come by symmetry, right. It has to satisfy these properties. Kij equal to kji, kii is greater than 0, and kii kjj minus kij square equal to 0. Therefore it is a positive definite matrix. It is positive definite, and why it has to be positive definite and all that basically comes from what is called the Onsager's principle. I do not have time to do that. That is another important concept. Have you studied this? Because somebody will get a doubt, sir, why should be like that? Why should ki should be greater than 0? Why should kij be equal to kji, and so on? All these questions will be answered by Onsager's principle. It starts from the assumption that it starts from the basic premise that you cannot violate the second law of thermodynamics and so on, right. When are these? Where will this be important? Anisotropic media occur, any laminated sheet basically is an anisotropic medium. Wood is anisotropic, transformer cores, there are many things where anisotropic media have to be studied. In fact, we are doing a project now for ISRO, Samarjit is working on that. So ISRO wants the measurement of thermal conductivity, anisotropic thermal conductivity of a laminated sheet. Okay, right now they are putting it into vacuum chamber and this thing, and it takes a long time. So we are suggesting some inverse technique and simultaneous estimation of these properties. So it is not just of academic interest, it is very important. Now the problem is the direction of heat flux is no longer normal to the isothermal surface throughout the point, and it is a lot more involved. Needless to say, there will be no further consideration of anisotropic media in this course. Okay. Now this is the introduction to conduction. So in the next class we will start with the energy equation, where the variable will be temperature. You will relate the temperature to the properties, and you will get a differential equation, partial differential equation for temperature, and then we will take simplifying conditions and reduce the equation, and we will try to get as many analytical solutions as possible. Okay.